Let's take a look at factoring this polynomial given a root in complex form. This is continuing in 3.4. So what if we had the polynomial x to the fourth minus 2x cubed plus 28x squared minus 4x plus 52, and we're given that 1 plus 5i is a root of f, and then to factor completely. So this is an application of the conjugate zero theorem. First, we note that all the coefficients of this polynomial are real, and we are given that 1 plus 5i is a root. So because of that, what we know is this. So since f is a polynomial with real coefficients, right, what I just pointed out, what we can say by the conjugate zero theorem didn't write that very well, did I? By the conjugate zero theorem, we know that the conjugate 1 minus 5i must also be a root. Let's say it like that. Must also be a root. Okay, so then find all zeros and factor completely. So what we're going to do is we're going to use synthetic division. So these are kind of the steps. So use synthetic division. To reduce the polynomial by 1 degree. And then once we've done that, we're going to apply again using the other root we know exists, which must be 1 minus 5i. Now, you got to be real careful with your organization with these complex numbers and stuff. So let's write it out. Start with the 1 plus 5i, so 1 plus 5i, and then we're going to divide into like this, and you write down the coefficients. Any terms missing? 4, 3, 2, 1, 0. So no terms missing. So 1. And then leave plenty of space. -2, 28, -4, and 52. Now, then leave space, right? Like that. What we know is this last term here must be 0. So I'm going to actually put that in first. That has to be 0 when you're done here. Okay, so let's do the product. Bring down the 1, multiply, and so it's 1 plus 5i. Okay, and then when you add, what do you get? So you're adding, right, just the real part, because there's only the real part for those coefficients. So that's just -1 plus 5i. And then we have to multiply this times this. And so you want to go, go to a scratched piece of paper or, to the side or something, and you're going to do 1 plus 5i times negative 1 plus 5i. And you're going to multiply that out. Okay, so what you get is negative 1 plus 5i minus 5i plus 25i squared, which equals negative 1 minus 25, which is equal to negative 26. So when you multiply right there, you get negative 26. Then you add and get 2. Then you multiply again, and you add, that one's easy. That's just 2 plus 10i. And then you add, and you get the negative 2 plus 10i. Okay, now lastly, we're going to multiply that and put it here. Now, what you know you should get negative 52, but of course, this is mathematics. You need to verify that. So you have 1 plus 5i multiplied by your negative 2 plus 10i. Multiply that out. Oh, I did a couple of things here. So I factored out the negative 2 first. 1 plus 5i. 1 minus 5i. And those are actually conjugates right there. That one. So now it's actually easier to multiply. You just have a squared minus b squared. So that's equal to negative 2 times 1 minus 25i squared. So that's going to be negative 2 times 26, which is negative 52. And of course it is, but that's what you're verifying. Okay. So next we take our other conjugate, which is the 1 minus 5i, do the same thing, and divide into that one. And you don't have to write it as a polynomial, you just basically do it. So let's write that down. So you have 1 minus 5i and you divide it into that. So now these are your coefficients that you put in next, just like you would have done by now with just the real cases. So you have let's see, we have 1 minus 1 plus 5i, 2, and negative 2 plus 10i. Last one will be a 0. It must be, and otherwise we did something wrong. So bring down the 1, multiply, which is 1 minus 5i. Add, get 0, multiply 0, put in a 0, multiply, and you get a 2 minus 10i. That one's a little easier, huh? And you add and get 0. Okay, so now this ends up being x squared plus 2. All right, and so this one, what you use is the square root the square root property. So square root property. And you have x squared is equal to negative 2. So you set this equal to 0 and solve, just like you would normally. And so x is equal to plus or minus, I'll show it to you. Okay, so you get always plus or minus the square root of negative 2, which is plus or minus I root 2. That's how you would write that. And so you have two cases. Those are your two roots. So let's count the roots. I think we're done, right? So 1, 2. So the roots are, of course, I root 2 and negative I root 2. So now you have 1, 2, 3, 4. How many roots does this polynomial have by the fundamental theorem or its corollaries, blah, blah, blah? It must have 4 roots because it matches the degree. So now let's just write this out, factor this completely. I mean, I have found the roots, but really we want you to show it in the factored form. So therefore, f of x is equal to, and then it's always x minus the root. So if we write this out, it's x minus, and we'll put it in parentheses because it's like the whole thing, the one that was given, 1 plus 5i, times x minus the other one, 1 minus 5i, times the next two, right, x minus I root 2, times x minus negative I root 2. And that's, I mean, you could simplify a bit there and all that, but that's good enough. Okay, so whatever the root is, you know the factor. It's x minus that root. And that's so it always works like that. Okay. So let's look at another example. So this will be basically a full example of find the zeros and multiplicity of f, factor completely, and graph. And I didn't say in this example, but I will. I'll edit it, I guess now. So I'll edit it and say by the rational root theorem. Okay, so example. So find the zeros and multiplicity of f factor completely and graph. So f of x, given that f of x is equal to x to the 5th. All right, so just automatically right now, you know the end behavior and orientation of that graph. So think about it. What does it look like? Leading coefficient, degree. Okay, you don't need to know the rest of them. But just by looking at that, because it's in descending order, we'll get to it in a second, but just it's automatic. It's kind of like what takes over in the long run, what's affected the most. Okay, so x to the 5th plus 6x cubed minus 2x squared minus 27x minus 18. All right, so we know n is equal to 5. Our leading coefficient a sub n is equal to 1. So that information implies what? Goes up on that side, down on that side. And automatic. Okay. Now, what I didn't say here, and I mentioned this when I wrote it up, but basically we want to apply the rational root theorem. So apply the rational root theorem. And just kind of an FYI, I'm moving on from the conjugate zero theorem and doing another example, basically how you apply a lot of the stuff we just did. So it's using the rational root theorem and getting into all that. Okay. So let's apply the rational root theorem. What do we know there? Actually, we can do the simple case stuff, like what is like f of 0? So we can do f of 0. It's negative 18. Okay, so it's way down there at when it crosses the y-axis, so that's the y-intercept. We know the behavior because of the leading coefficient and the degree. We know there are how many roots are there? So this means there's 5 roots. Does that mean it crosses the x-axis 5 times? Not necessarily. Okay, because remember, they can be complex. So if you have a complex root, that is not on the x-axis, so you may not cross there. So it tells us that it has 5, but they could be complex, so wouldn't worry about that. Okay, so let's now apply the rational root theorem. So we have a sub n is 1. My a naught is negative 18. And remember the order, right? It's always the factors of negative 18 over factors of the leading coefficient. So a naught plus or minus 18 plus or minus 9 plus or minus 6 plus or minus 3 plus or minus 2 plus or minus 1. And then, of course, a sub n, the leading coefficient, is simple. It's just plus or minus 1. So it's really just the top one, right? All right, so there's a lot to pick from. You kind of want to look at how big of numbers these are. So if you put an 18 and raise it to the 5th power, there's really nothing over here to counteract that. So it might be too big. You want to start with more simple numbers. And there's no real good rhyme or reason of how to start. And there are other things we can look at, but I basically will give you some hints and make it a little more simple. But let's just suppose, so this is kind of how you'd go. Suppose we try 3. 3 seems reasonable. So let's try 3, applying the select division. So 1, missing term is 0, 6, negative 2, negative 27, and negative 18. So we don't know if that's going to work or not. Again, what are we looking for if it does, quote, work? 0 remainder, right? So this is a 0 remainder, then yay, it worked. That means it's a factor and a 0. Okay, so that's what you're looking for. So bring down the 1, multiply, add, multiply, add, multiply, add, multiply. Is this going to work? Pretty much obviously not, huh? Okay, nope. You don't even care. It's not going to work. Then you go on to the next one. Don't erase this. You know, if you do all this work, don't go back and erase. Just leave it. Just cross it out and go on. You want to show, I want to see what you tried, you know, that kind of thing. Let's suppose you tried negative 1. Okay, and so you would just try the next one, you know, 6. I mean, you try kind of the middle ones usually first. All right, so write all those down. 1, 0, 6, negative 2, negative 27, negative 18. Draw on your little mark here. Okay, so question mark. So is that 0? No. Okay, this one's, we'll check it out. Okay, so bring down so try it. Okay, so I'll, pause this thing and try it. See if it works. And we're back, so bring down the 1, multiply, add, multiply, add, multiply, add, multiply, add. Oh, look. Multiply and add. Yay, that worked. Okay, so that worked. 0 remainder. So now, and you wouldn't necessarily write this here, but I just want to show you exactly what's happening. So that means you get x minus negative 1 as a factor. And then this is another polynomial. that's reduced by 1 degree. So now that's x to the 4th minus x cubed plus 7x squared minus 9x minus 18. Then you keep going. Now you don't choose more factors, right? I mean, 19's still there. I mean, it's the same ones you choose. You cross out the ones you tried. But if it was a factor for the first one, it's going to be a factor for the other one as well. Okay, so, and you keep going. You may fail a lot, but that's okay. You're still learning the process. So let's try 2. 2 does work. Just to speed things up. Okay, so go through that, try it, see if it works, which it should. So this should be a 0. Bring down the 1, multiply, add. 18. Okay, and then you get 0. So now what you get on this one is you have f of x equal to x plus 1. Now this is the factor x minus 2. And then we have x cubed plus x squared plus 9x plus 9. Now that's kind of a nice special form. Now this is a particular case, and it's a special case, special form. These have common factors, and so does this. And so we can use factor by grouping. So you factor this as x squared times x plus 1 plus 9 times x plus 1. And then you have that in common to each of those two terms, and then you factor that. So this is x plus 1, x minus 2, x squared. I'll usually do it like this. So you're factoring out the x plus 1, and you're left with x squared plus 9. Well, x squared plus 9, that is a irreducible quadratic. So we call this, the form right here, is irreducible quadratic over the reals. I guess you don't need to say that. I mean, you can write it down now, but that's going to factor in a different way. So if you find the roots of that, x squared plus 9, you can apply the square root property again, and you're going to get plus or minus 3i out of that one. So if those are your roots, then x plus 3i and x minus 3i are your factors. So now this is factored completely. We have f of x equal to x plus 1. You can see its quantity squared times x minus 2. And then you have the complex cases, the imaginary cases. So you have x plus 3i and x minus 3i. And so those will not show up on the graph, like when you graph it in the real number plane, the real plane, it doesn't show up. So let's write down the roots. So the roots are -1 with multiplicity 2, 2 with multiplicity 1, and that's it. You don't write down the other ones. Okay, so plus or minus 3i are not real roots, therefore not x-intercepts. Okay, so essentially we just don't graph those, but it is factored completely. I already did f of 0 up there, so now we can graph it. Now here's the big deal. We graph this thing. And we'll do it nice and big here. Should probably stop the video after this one. Okay, so x and y. Let's see if I can change the template. Actually, it usually doesn't line up as well, but I'm going to try it anyway. It's easier to graph. We'll just move them around. Okay. So let's just do that. Why not? All right. So here's your X, here's your Y. And so let's go ahead and graph. So we have, let's label what we know. What do we know? So let's first do the in behavior. So you just, this is, you're going to erase this later, but we know what does that. Let's do the y-intercept. Now, the y-intercept, I mean, it's like negative 18. Don't put it down there, negative. Just write it, just put it like right there. And just say that's negative 18. Okay. Then at negative 1, so I'll call this negative 1, and 1, 2. So at negative 1, what does the graph do? So it's down here. It must be down here to the left because it has a 5th degree and a leading coefficient of positive. So it comes up, and does it cross that? Or what does it do? It tells you right there. What does it do? That tells me it bounces, right? So it's on the bottom, so it must come up, just touch and go back down. And then what must it do? Well, then it has to keep going and cross through the negative 18. Then what about the multiplicity of 2? Well, it has to be odd because it has to cross it and keep going up like that. So that's what the graph must look like. So it must come up, bounce off negative 1, turn, come back down, cross it at negative 18, go back up, cross it 2, and keep going, just like that. You can leave these things or just cross them out. Okay, so I'm going to erase them, but you want to make it look somewhat nice like that. And then the graph somewhere might do other turns and twists and stuff, but that's all it can do. It only can do one more dip like that. But it does not, it cannot, it may not cross the x-axis at any other place or touch any other place than negative 1 and 2. That is fixed. That is the only place you have. Okay, this graph must look like that. There's no reason to plot points or get on a calculator or do anything like that. It's kind of, I wouldn't say meaningless, but we just don't do that. Okay. There's a couple, so practice more examples just like that. This would be quite a hefty one on an exam, but this, this could be asked, this type of thing. Right there, this one right here could be asked something like that. Factor completely, apply stuff. This one's a little long. I would never ask this many questions on an exam, even a take-home, but it could. Okay. We will stop there, and the last thing we'll do is, in the next video, Descartes rule of sign, and that'll be it.